Okay, here are your solutions to 4-8. These are the guided practice problems. Problem number 1, they tell us the function a equals 2/10 v squared models the acceleration of a carnival ride, where a is the acceleration toward the center of the ride in meters per second every second, and v is the velocity in meters per second. Graph this function, then use your graph to estimate the velocity of the ride at an acceleration of 1 meter per second every second. So let's take this a step at a time. The first thing that we probably ought to do is put some labels on this. So A is our output, and this says that A is the acceleration toward the center of the ride in meters per second every second. So A is the output. That would put it on this axis here, and our output, they said, is A, which is acceleration. I'm just going to put ACC. Okay, and that is in meters per second, and the way to put that is per second squared. This is something you'll learn in science, but that's good for now. Now our input is V for velocity, and that's in meters per second. So here we're going to have velocity, I'm just going to abbreviate again, and that's in meters per second. Just 1 second. This is per second, this is per second. Now we need to create an input-output table, or a function table, I should learn to call this. So again, we said that our input is velocity, so that's going to be V. Our equation is 0.2, or 2/10 times V squared. And our output, I don't know how that ended up there, but we'll just write over it. Our output is A, acceleration. And we're not going to have to make very many calculations here, and you'll see why in a minute. But obviously we're going to start with 0. So if we take 2/10, now I'm going to draw an arrow here so I don't have to try and write these decimals, 2/10 times 0 squared, and then we're going to have an input of 1, 2, and 3 here. This is as far as we're going to go. So here we're going to have 1 squared, 2 squared, and 3 squared. Well, we can do this math in our head, believe it or not, because 2/10 times 0 is, of course, 0. Here we have 2/10 times 1 times 1, so 2/10 times 1 is 2/10. And here we have 2/10 finally times a number that we actually have to do some thinking. 2 times 2 is, of course, 4. 4 times 2/10, 4 times 2 is 8, so 4 times 2/10 would be 8/10. And then lastly, we have 3 times 3 is 9, times 2/10 is 1.8. So there are our coordinates that we're going to graph. So first of all, we can put our first point right here at 0, 0. The second point we want to plot is at 1 and then at 2/10. So we come over here to 1 and rise up to 2/10, and they used a nice scale here. They're counting by 2/10, which makes sense because, as you can see, all of our values are going to be like that because of our input of multiplying by 2/10. So we're right here at 2/10. Next, we're going to do 2 and 8/10, so we're at 2 and up to 8/10. And lastly, we're at 3 and up to 1.8, or 1 and 8/10. So there are our 4 points, and you can see we have a nice parabola sloping upward like this. So now, in order to make this easy to see, we'll turn on our magic answers, and notice that we have an acceleration here of meters per second squared, velocity meters per second, and then we have our points plotted just like I had before. Notice that they did a nice job here of labeling their equation, which is something we should do, and we only have one thing left to do. They asked us to graph it. We did it. And then it says, use your graph to estimate the velocity of the ride at an acceleration of 1 meter per second every second. In other words, 1 meter per second per second. So we're taking a look at this point right here. So we're going to move across here at 1 and recognize that we're going to be a little past 2. So they said about 2.2 meters per second, or MPS, meters per second. Now let's take a look at problem number 2. For problem number 2, we can create an input-output table. So we have an input of x because it's right here. So that means we're going to have 3 times x squared, and then an output, of course, of y. And we're going to do really simple values so we can do most of this in our head. We're going to put in a 0. Well, 3 times 0, of course, is 0. And we're going to put an input of 1. That's 3 times 1 squared. 3 times 1 is 3. Put an input of 2. And that's going to give us an output of 3 times 2 squared. It's 3 times 4, which is 12. And I can see I'm already not going to fit any more than that here because you can see our y's only go as high as 12. So now I'm going to remember that I can also consider that I put in a -1, and I'll get the same output, and a -2 in the same output. So I can graph the point 0, 0, which is going to be right here. I can graph both the point -1 and 3 and +1 and 3. So -1, notice our scale here. We're counting by 2's here because it's -4 here already, so this line here would be -2, so -1 would be only halfway over, and +3 would be up between the 2 and the 4, so that's going to be right about here. And this is going to be a little bit difficult to see. It should be right in the middle of here, and for some reason my pen just will not draw points very easily. I have to make these great big blobs. And that's why it's important that we went up as high as the 12. So now we can go to 2, which is right on the line, and up to 12 here. That would be -2, 12 there, and +2, 12 there. And we can see that we've got a pretty tight opening upward parabola. Now we can do the same thing with number 3, create an input-output table. We would have x, here we would have -5 times our x squared, and we'd have an output of y. So if we put in 0, it's -5. I'm just going to draw an arrow here. -5 times 0 squared is going to be 0. Here I'm going to put in 1, so I'm going to multiply by 1 squared. So -5 times 1 is -5. Here I'm going to put in 2. So I have 2 squared here is 4. 2 squared is 4. So it's -5 times 4 is -20. And clearly we aren't going to fit any more on our scale here, so we can stop there. So we have a point here at 0, 0. And then don't forget, you are also plotting the same values for -1 and -2. So if we go to -1, we're going to go to -5. So -1. On this, you got to be really careful here, because here you can see we're counting by 1s. This would be -1, but here we're counting by 2s. So we're at -1, down to 4 would be there, and 5 would be right about there. And we have a point right straight across from it at +1, -5. And then we have +2, -20, which would be way down here somewhere. So let's just kind of estimate where that would be. If we had +2 down to -20, it'd be down in this range somewhere. And at -2, we would be down over here somewhere. And we would have a downward facing parabola. So don't forget, you need to know how to create these tables of values, because when we correct these in class, we're going to make sure, for example, with this one, I would tell you that this particular point here and here needs to be accurate on your graph, or you're not going to, you're showing that you don't really truly understand how to get this, that you just plugged it into a graphing calculator and then sloppily wrote something down. That's not acceptable. It needs to be accurate. So now in showing that, let's take a look at exactly how this should be. So I'm going to say again, when we would correct this in class, I would say that their graph needs to go through the points -2, +12, and +2, +12. And on this one here, I would probably choose these 2 points here and here to check for accuracy. Problem number 4, building on the essential question, when does the graph of a quadratic function open upward or downward? Real quick, easy answer here, and this is something that definitely ought to be on your gold sheet, the graph opens upward if the coefficient of the variable that is squared, so let's talk about the x squared because it's almost always going to be x squared for these first several problems. If it's positive, it opens up. If it's negative, it opens down. And that's how I would put that on my gold sheet. Please do independent practice.